Dear Mr. Prakash, hey, it's me, JPEC, and I hope you remember that question I asked you before winter break. I asked you about the algebraic proof of the variance of a distribution x and the mean of a distribution x, where x is a Bernoulli random variable or a binomial distribution. And you told me that in the textbook, there is an intuitive proof or reasoning for these two equations. Ah, what an elegant solution. But sorry, the thing is...
Don't care, still don't care.
See, if you watched 3 Blue 1 Brown's video about Alice and Bob, I personally learned that rigorous algebraic proofs are much cooler than easy intuitive solutions. Yeah, Alice's method is kinda cool, but in my opinion, it does not top Bob's long and strenuous calculations. So today, I'll be proving the formulas for the mean and variance of a binomial random variable. And without further ado, let's get started. So first, we begin with the definition of a mean for distribution x, a binomial random variable, with n trials, and with a probability p. The mean mu of x is the sum of k equals 0 to n for x of k times p of k. And since this is a binomial random variable, x of k is just k. And p of k is this long expression, which is n choose k times p to the power of k times 1 minus p to the power of n minus k. And if k equals 0, then the entire term will be equal to 0. So k equals 0 is negligible, and we could change it to k equals 1. Next, let's just expand this combination notation into the fraction n factorial over k factorial times n minus k factorial. And then, let's now decompose the factorials. N factorial into n times n minus 1 factorial, and k factorial into k times k minus 1 factorial. And finally, let's decompose p to the k into p times p to the k minus 1. And finally, we can see here that the two expressions are still equivalent. Next, we can cancel out the first k with a k in the denominator. And then we could factor out n and p out of the summation because they are not related to k. Then, let's just substitute n minus k with n minus 1 minus k minus 1. And it's just a surprise tool that will help us later. Now, if you know something a little about binomial theorem, you'll see that there are some consistencies that line up with the expression that we got and the binomial theorem equation. Before we do that, choose 2 letters, say epsilon and delta. Let epsilon equal n minus 1 and delta equal k minus 1. And now let's change the bounds. When k equals 1, then we know that delta is equal to k minus 1, so delta is equal to 0. And when k equals n, then delta is equal to n minus 1, which is equal to epsilon. Then let's just substitute every single n minus 1 with an epsilon and every single k minus 1 with a delta in the expression. Therefore, we get np times the summation from delta equals 0 all the way to epsilon for epsilon factorial divided by delta factorial times epsilon minus delta factorial times p to the power of delta multiplied by 1 minus p to the power of epsilon minus delta. Then we could see that epsilon factorial divided by delta factorial times epsilon minus delta factorial is just the expression for a combination. So we could change that to epsilon choose delta. And we can see that our final summation expression is basically equivalent to that of a binomial theorem expression, where it is 0 through a certain number, and then there's a combination, and then certain values raised to a certain exponent with just some changed symbols and letters. So we can express the entire summation as the following. We let 1 minus p act as the a, and p act as the b, and then let epsilon act as the n in the binomial expression. And then we could finally convert the entire summation to 1 minus p plus p to the power of epsilon. And we know that 1 minus p plus p is 1, and 1 to any power will just be equal to 1. Therefore, we end up with the mean being equal to n times p. Now that we've found the mean, we can finally prove for the variance of a random distribution by using a very similar technique that we used previously. First, we define the variance of a distribution x with n trials and the probability p to be sigma sub x squared. And this is equal to the sum from k equals 0 to n of the expression x minus x bar, which is the mean, or mu of k, and that expression squared multiplied by p sub k, or the probability. And we know that x bar, or mu of x, or the mean, is equivalent to just n times p. So we can just substitute np for x bar, and then we could just expand the binomial, and then distribute the p. Then we can distribute the sum into multiple summations. Then we could factor out certain parts of the expression that are unrelated to k. And since this is a binomial distribution, we could substitute x of k with just k. Then, in the second term, we could see that the summation is exactly the same as mu of x, or just the expression summation of the mean. So we could just substitute that with np. And for the last summation, it's the sum of all probabilities of the distribution, which should just be equal to 100% or just 1. If we simplify everything, we get that the sum of k equals 0 to n for the expression k squared times p of k, subtracted by n squared p squared. Now we end up in a position where the variance is equal to this expression, and the second term is really easy to decipher, it's just the mean squared. But what is the second term? How can we figure this out? Let's take this to a separate window, and let's do a little bit of algebraic manipulation and add k times p of k and subtract k times p sub k. Then let's rearrange the terms a little bit and factor some like terms, and then we get this expression. The summation of k equals 0 to n of the expression k times k minus 1 times p of k, plus the summation of k equals 0 to n of the expression k times p of k. And we realize that the second expression is just the mean. Now again, you have no idea what the first expression evaluates to. However, you realize that there's a little pattern that the front two terms correlate to some kind of factorial. I find the correlation a little suspicious, so I decide to dig a little deeper. So now it's back to the old shebang. I substitute p of k with its probability function, and if k equals 0 or 1, then the entire expression is just 0. So we can set the lower bound to k equals 2. Then I expand the combination into its expression, and I think we all know where this is going. You decompose the factorials and the exponent, then you cancel some stuff out, you factor out the n's and p's, and then you change n minus k into n minus 2 minus n minus k, and then you could finally change everything into the terms of epsilon and delta, where epsilon is n minus 2 and delta is k minus 2. And then we go retrieve the binomial theorem, and then convert the entire summation into 1 minus p plus p to the power of epsilon, and then we get the final answer, n times p squared times n minus 1. Therefore, the sum of k equals 0 to n of the expression k times k minus 1 times p of k is np squared times n minus 1. And we could take this all the way back to the previous Microsoft Paint we move it to another window, and then we can finally solve for the sum of k squared times pk. We find that the sum of k equals 0 to n of the expression k squared times pk is n squared p squared minus np squared plus np. Then we could substitute that expression into the first expression we got to describe the variance of a binomial distribution. And we finally get that it's n times p times 1 minus p. And there you have it, the algebraic proof of the mean and variance of a binomial distribution. I hope you all found this video interesting and enjoyable, and I hope you learned that always, algebra is better. If you're asking why go so far to create a video on this topic, it's because I genuinely was not satisfied with that proof that the textbook gave me. It was just boring. Anyway, thanks for watching. Sincerely, JPEG.